Okay, we're doing Unit 6, Section 1, Day 3 today. We're going to start with this warm-up. We're solving the given linear program, graph to find the feasible region, identify the objective function, constraints, max, min values. So this is what we did on Day 2. This first guy is going to be our objective function. The objective function is usually finding a C or a P, usually for cost or profit. These four functions right here are going to represent our constraints. And we're going to need to graph these. So we want x values greater than or equal to 0. That's going to be a straight vertical line through the x value of 0. Y values, this should be less than or equal to 4, or else the problem will not work. So y value is less than or equal to 4. And then these guys right here, you're going to need to put in the y equals mx plus b form. If I subtract over the 2x, divide by 2, for this guy, you're going to end up getting something like y values less than or equal to negative x plus 5. For this guy, you should get something like y values greater than or equal to x over 3 plus 1. Don't forget the sign flips when you divide over a negative. So if I graph him, he's going to have a y-intercept of 5, then down 1 over 1, all the way down. If I graph him, y-intercept of 1, then sort of up 1 over 3, up 1 over 3. All right. We need to shade our feasible region, and this one's a little confusing. It looks like we have sort of 1, 2, 3 possible regions that could be the feasible region. So we need to think about where we would shade, where all four of these functions sort of make sense. It's sort of in our best interest to look at the two with the y equals mx plus b formats to sort of help us out. So this first guy represented this line, and it was less than or equal. So we would shade below this. So it's either going to be this region or this region. And then we have this guy, y value is greater than or equal to x plus 3 plus 1. So that's this guy, and it's greater than, so it's going to be above it. So that doesn't help narrow it down because it could still be this or this. So this is why I wanted us to change this to be less than or equal to 4. So if I do y values less than or equal to 4, this would be below it. And so we're talking about this region right here. If I do my intersection points, we have intersection points at 0, 1, 0, 4, 1, 4, and 3, 2. And if I plug into the objective function, we're going to find, so remember we sort of plug in for each one of these. I don't know why I'm writing it out of order, but I am. So I put these in a different order than I did up here. No big deal. If I plug in 0 for x and 4 for y, we're going to get something like 8. If I plug in 0 for x and 1 for y, we're going to get something like 2. 3 for x, 2 for y, you should get 19. And 1 for x, 4 for y, you should get 13. So our minimum value is 2. That occurs at 0, 1. And our maximum value is 19. That occurs at 3, 2. All right. That's the warm-up. Today we're going to be looking more at the word problems that sort of go along with this linear programming. In order to do this, I have some steps here. We're just going to sort of fill this in. First step is going to be to assign variables to each quantity that is being solved for. We're going to have an x and a y. We're then going to write our objective function first. And the objective function is going to be the equation for the quantity that we either want to minimize or maximize. We're then going to write the constraints of our function, and the constraints are going to be inequalities. And we're going to graph the constraints. Once we graph the constraints, we're going to calculate the coordinates of the vertices. That's sort of the intersection points. I don't think there's an I there. And no, there's not. Evaluate the coordinates of the vertices into the objective function. So then we're going to take our intersection points and we're going to plug them into the objective function to figure out what our maximum and minimum value is. All right, so if I flip over, we have 3 examples today, but they're all kind of long. The first example here is a word problem. We got a carpentry shop that makes dinner tables and coffee tables. Each week, the shop must complete at least 1 dinner table and 4 coffee tables to be shipped to furniture stores. The shop can produce at most 18 dinner tables and coffee tables combined each week. If the shop sells dinner tables for $150 and coffee tables for $120, how many of each item should be produced for a maximum weekly income? All right, so first thing we want to do is assign variables to sort of the 2 things that the problem's talking about, and we are talking about dinner tables and coffee tables. We're making money off of them. We're talking about how many we have to make each week, and we sort of, at most, we can only make 18 of these. So the 2 things that are sort of being thrown around the most, that's going to be your variables. So we're going to say dinner tables and coffee tables. Those are our variables. We are trying to figure out how much of those we need to make. Our objective function is going to be the function that sort of maximizes or minimizes whatever it's asking for. So the question is, if the shop sells dinner tables for $150 and coffee tables for $120, how many of each item should be produced for a maximum weekly income? So we're going to set this up as a profit equation. All right, we're trying to figure out what's the most profit we can get. And we're going to say however many dinner tables we sell, we get $150 per dinner table. And however many coffee tables we sell, we get $120 per coffee table. Now we have to do our constraints. There are sort of 2 nice, easy constraints here, although it's sort of hard to see. It says each week the shop must complete at least 1 dinner table. So if I have to make at least 1 dinner table every week, our x values have to be greater than or equal to 1. We can't be less than 1 apparently. We have to make at least 1 dinner table. We have to also make at least 4 coffee tables. So our y value has to be greater than or equal to 4. We cannot be less than 4. We are compelled to make 4 coffee tables. So this last one is going to use this other bit of information they give us. It says the shop can produce at most 18 dinner tables and coffee tables combined. So that means if we add up our dinner tables and coffee tables made each week, it has to be less than or equal to 18, because that's the most we can make. So x plus y has to be less than or equal to 18. However many we make, it has to be less than or equal to 18. All right, we want to graph these now. So we have our 3 constraints. We're going to graph x equals 1. We're going to graph y equals 4. This guy we're going to want to put in y equals mx plus b form, so I'm going to subtract over the x and get y is less than or equal to negative x plus 18. So a y-intercept of 18 and sort of a down 1 over 1. This is obnoxious. All right. Our feasible region, we don't have to think too hard about this. There's only one region that's enclosed by all of these lines. And so our intersection points, we got 1 intersection point down here at 1,4, 1 intersection point up here at 117, and 1 intersection point over here at 14,4. So intersection points 1,4 117, 14.4. All right, now we got to do our maximum weekly income. So which of these points, if we plug into our profit, is going to maximize our income? So it seems kind of silly to do 1, 4, but let's just do it just in case. So if I plug in 1 for x and 4 for y, 150 plus 120 times 4, I get 630. If I plug in 1 and 17, so if I plug in 1 for x and 17 for y, I'm going to get $2,190. All right, and then our last one, if we plug in 14 and 4, if I plug that in, we get $2,580. So our maximum weekly income is $2,580. And in order to get that, what should, how many dinner tables and how many coffee tables should we be making? We should be making 14 dinner tables. So that's our X value, and X represented dinner tables. And we should be making 4 coffee tables. That was our Y value, and that's what Y represented. All right, let's get to example 2. You are the owner of a new pet store. Congrats, you sell only lizards and rabbits. You must have at least 1 lizard and 6 rabbits in the store. Okay. You make a profit of $25 per lizard and $10 per rabbit. You can have no more than 20 pets in your store. What is the maximum profit that you could make? How many rabbits and lizards would you have to sell? So this one's very similar to the previous example. If you want to hit pause and try it on your own, feel free. I'm going to go ahead and start this here. So X is going to be our lizards, and Y is going to be our rabbits. And our objective function is going to have something to do with maximizing our profit. So profit's going to equal, let's see here, we make $25 off the lizards and $10 off the rabbits. So 25 times X plus 10 times Y. We got some silly constraints here. For some reason, we have to have at least 1 lizard in the store. So X values have to be greater than or equal to 1. And for rabbits, we have to have at least 6 rabbits in the store. So Y values have to be greater than or equal to 6 reasons. And then we can have no more than 20 pets in the store. So our number of lizards plus our number of rabbits have to be less than or equal to 20. All right. This one we'd want to get in y equals mx plus b form. It's going to be y is less than or equal to negative x plus 20. And so if I graph this, there's x greater than or equal to 1. Y is greater than or equal to 6. And then this negative x plus 20. This is so obnoxious. All right. And it looks like we're going to have intersection points at 1, 6, 119, and 14, 6. So 1, 6, 119, 14, 6. You could plug in, you'd want to plug in each of these into your profit to test it. I'm going to go ahead and say that our maximum profit ended up being $410. And that was with the 14, 6. So selling 14 lizards and 6 rabbits. Not a great business. All right, if you flip over, we only have one more example. And you might be thinking this seems kind of easy so far, at least with the constraints being pretty simple to find. This last example is kind of tough. So, for this last one, we got 2 manufacturing plants making the same kind of motorcycle. The table gives you hours of general labor and technical labor required to make one motorcycle in each plant. We'll come back to this table in a minute. Plant A cannot produce more than 4 motorcycles for the 2 plants combined. The manufacturer can afford to use up to 48 hours of general labor and up to 22 hours of technical labor per week. And let's see here. And that was for the two plants combined. And then Plant A earns a profit of $8 per motorcycle, and Plant B earns a profit of $5 per motorcycle. How many motorcycles per week should the manufacturer produce to maximize their profit? Okay, so X, even though it says we're making the same kind of motorcycle, we have sort of two different motorcycles we're talking about. We have Plant A motorcycles and we have Plant B motorcycles. So I'm going to let X be Plant A motorcycles. Ugh. And I'm going to let Y be Plant B motorcycles. Our objective function needs to have something to do with what we're trying to maximize, and we were trying to still, just like the previous two problems, maximize the profit. And so our profit will equal, we make $8 off of the Plant A motorcycles and $5 off of the Plant B motorcycles. So we'll say 8x plus 5y for our profit function. All right, now for our constraints. And this is going to seem, so there's sort of this first obvious one that kind of like what we had with the with the pet store and the other problem. It says Plant A cannot produce more than 4 motorcycles. So we can't make more than 4 motorcycles for X, so our X values must be less than or equal to 4. After that, it talks about the amount of hours we can use for our general labor and 22 hours for our technical labor. And we're going to have to use this table for this. So for general labor, Plant A uses 9 hours per motorcycle and Plant B uses 3 hours per motorcycle. And at most, we can use up to 48 hours of general labor. So we're going to say something like this: 9x plus 3y. So 9 hours per general labor at Plant A plus 3 hours of general labor at Plant B. Well, we have to be less than or equal to 48 hours of general labor overall. Technical labor, we want to sort of do the same way. We can have up to 22 hours of technical labor. And so if I use the sort of the same idea here, 1x plus 2y must be less than or equal to 22. All right, there are 2 more constraints, and there's no other information in the problem. So what is this? Why do we have 2 constraints here? We didn't have these on the other examples. It's because on this example, it doesn't state what's the least amount of motorcycles we have to make every day. You know, the previous 2 examples said we had to have this many pets in the pet store, or we had to have this many tables going out, but this doesn't say how many motorcycles we have to make each day at the plant. And this is an obvious answer. We have to make at least 0 motorcycles at each plant. So our Y has to be greater than or equal to 0, and our X has to be greater than or equal to 0. We cannot make negative motorcycles. So if they don't tell you the least amount that you can make, you need to include the greater than or equal to 0 functions for X and Y. All right, we're going to need to graph these. These 3 graphs will be pretty easy. This guy, he's going to end up going to y is less than or equal to negative 3x plus 16. Feel free to check me. And this guy, he's going to go to y is less than or equal to negative x over 2 plus 11. So if you put those in y equals mx plus b form, that's what we get. So if we graph these, I'm going to graph my 3 easy constraints first. X is greater than or equal to 0. The y is greater than or equal to 0. And x is less than or equal to 4. So those are the 3 easy ones. Oh, sorry. Those are the 3 easy ones. And then we have these 2 functions right here. He has a y-intercept of 16. He's going down 3 over 1. The grid here is kind of funky with the rectangles. And then this guy right here, that's the 11, and then sort of down 1 over 2. Oop. All right, and we got multiple regions going on here. We got sort of 1, 2, 3, 4 possible regions this could be. It's going to be a good idea to shade so we know exactly which region we need to find the intersection points of. If I go back and look at these two functions, the negative 3x plus 16, that was this one. We want y values less than that, so it would be this side right here, so it can't be this guy. And then for him right here, we want y values less than or equal to this function, that was this line, so it's going to be underneath him as well, so it can't be this guy. It's either going to be this or this. And so I'm going to go back to this other constraint, x values less than or equal to 4. So here is that line, less than would be to the left. So we're talking about this region right here. All right, so what are our intersection points? We have an intersection point at 0, 0. We have an intersection point at 0, 11. We have an intersection point at 210. We have an intersection point at 4, 4. And we have an intersection point at 4, 0. And we need to check all of these. And we're going to plug them back into this profit function. And I'll just go ahead and write which one ended up working. I'm going to assume you know how to check it. What ends up working is the 210. So the 210 produces $66. That ends up being the most you make from your motorcycle plant. The pet store is doing better than you. And then your maximum motorcycles produced. So we're producing 2 plus 10, we're producing 12 motorcycles. That's our answer. All right. That ends the notes for today, and I will put up a video for the classwork as well. Don't forget to go take your daily quiz, and the classwork is your work tomorrow. All right, have a good day.